So there's a lot of emphasis on getting rid of the flame retardant chemicals, but not nearly as much as addressing the fire risk. So fire risks in society, as I kind of showed at the beginning, NFPA would argue that yes, it's important to provide fire protection to address the 11.6 billion in damages, 3,000 dead per year, but the flame retardant chemical phobia suggests, well, no, it's not an acceptable risk. Let's just get rid of it. And this comes back to life in general. Life is risk. What is an acceptable risk? Society, to some point, has to make a decision on what level of risk we're willing to live with. So it's not a black and white issue. If fire protection is gained, but potential environmental damage later, is that an acceptable trade-off? Is it better to let things burn and let them be easier recycled? Is that an acceptable trade-off? What about natural fires? How to address those issues with those? What's the acceptable risk there? So every time in history there's been a major fire, kind of going back to all those things I showed at the very, very beginning, those major events in fire history, the reaction, and it's always been reactive, we can't foresee what the fire problems are going to be, is to address it rather than let it slide. So again, the study of history is, those who forget their history are condemned to repeat it. I believe that was, I don't remember which philosopher said that, but why ignore history? If there's an environmental problem, why not address it by coming up with new flame retardants? Again, new science and new problems, so the flame retardants are into the environment, either due to spills, leaching of the product in its life cycle, routes we haven't even figured out yet. So maybe one particular solution is reactive flame retardants into the polymer itself. If they're getting out, let's prevent them from getting out. And you can see a kind of schematic of this. Sorry, I'm showing organic chemistry. So there's the flame retardant, just kind of blended into the polymer, and there it is kind of connected into the polymer. If you react the flame retardant into the polymer, it is a much harder time of getting out. It can't leach in the environment, and in many cases, you're starting to see this approach become commercially available for a lot of things. You'll see it in circuit boards today, for example. For circuit boards, reactive flame retardants are in use today. So the solution grows great promise, but there's increased manufacturing because it's new. It may change recycling of the product. Maybe you can't always just regrind and recycle. You may have to incinerate foam for waste energy processes. Again, you're thinking about total life cycle assessment. How am I going to handle this? Okay, I've got a new product. Well, if I've now flame retarded it so well that it doesn't burn, maybe I can't do waste energy anymore, and I have to think about a different way of addressing it. So it's not a panacea either. So now let me tell you about some of the UDRI solutions that we've been working on to address some of these issues. There's two that we've been working on. One has been in collaboration with Texas A&M. They had discovered a very interesting coatings approach of polymer nanotechnology. They weren't fire guys, though. They had kind of played around with it and kind of understood, hey, this looks like it shows some promise. So people like myself kind of partnered with them to help them make it better and quantify its performance. And then some reactive flame retardants that I've been doing here with Professor Bennon and the UD Chemistry Department. So let me just, these technologies I'm separating separately, and I'm talking about today, but because of their promise, we're going to combine them later. So this is the layer by layer coatings or nanotechnology, and what it is you literally build up one layer of a nanopolymer nanocomposite at a time, hence the term layer by layer, up onto the material, and it's a conformal coating for a fabric or a foam. Seems to work on both. And so you can just kind of looking at the number of bilayers of this nanocomposite increase. So there's what it looks like after it's burned with 5, 10, and there's the flame damage after 20 bilayers. So this is on a fabric. And you can kind of look at it here. You can see a little bit of the flame picture. So that's only 5, not enough fire protection. 10, pretty good. 20, there's very little fire damage. So why is that significant? So there's what the stuff looks like before. Doesn't look that different than the control. The fibers look just about the same even after 20 bilayers. But then you burn it. Well, there's nothing left from the control. Straight cotton burns to nothing. But with the nanoparticles, it's still intact as the fabric. So there's no potential of dripping and sticking to skin when you have a burn. Indeed, many clothing fires result in second and third degree burns because the fabric melts and sticks to skin. You can kind of prevent this from happening. Yeah, you may still have a first degree burn or maybe worst case a second degree, but usually once you get third degree burns, you may survive that for a little bit from the infection from the damage to your skin later on is what will kill you. So new flame retardant chemistry. So this is what I've been doing with Professor Bennon. Made a lot of different new chemistry structures, all potentially able to react into polyurethanes. And we found one that seems to show some promise. It addresses this drip back phenomena. So again, I told you we need to address the heat release thing of polyurethanes. We also need to kind of prevent those materials from dripping and flowing. Normal polyurethane shows a two-peak behavior, and I don't have that here due to space, but it's a very high heat release. So it's maybe all the way kind of up here. I've now dropped it down to here, but what's more important is there's the base polymer, melts and flows and chars, And then here's this one. Because of that group right there, that chemical group, causes it shrinks up rather than melting and flowing and collapsing. Obviously a lot more that we need to do to advance it and commercialize it, but it does show some promise. So possible, anti-drip in larger scale fire tests. So let me just kind of conclude with the future of fire protection. And again, I've kind of covered a wide variety of different issues, politics and everything else. So predictions for the future. So now I'm telepathic and I can see the future. Yeah, remember what I said earlier about Einstein, right? We're still going to be in a reactive mode on fire risk. We may be able to foresee certain fire risks as they occur. People start inserting more plastics in the home. Hey, batteries here, power supplies here, whatever else. We, as fire safety engineers, may see that that's a problem, but we can't always, we're always going to be in reactive mode. We're never going to be able to address problems before they occur. And we're probably going to have big fire losses. We're still going to have them. I mean, we always have, we always will. Indeed, the black humor in my circle is that if we need an increase in funding, there just needs to be a couple more really big fires. And there'll be an increase in funding, because that is how funding is done in the United States, and probably even worldwide, for fire safety protection. Oh God, we have a problem, let's put money on it. Problem solved, money goes away. Fire safety is treated a lot like security was before 9/11. Everyone thinks it's important, but no one's willing to pay for it until you have a fire. So fire risk and losses will probably start to increase again before they decrease due to this flame retardant chemical phobia, especially since we're trying to come up with fuel savings. We're trying to come up with energy savings. So let's start putting more plastics in cars and composites and everything else, and aircraft. Well, that's good. We're lowering our carbon footprint. We're increasing our energy efficiency. But a lot of those plastics are far more flammable than metals and everything else. So the fire risk is going to increase because there's now effectively more fuel everywhere there's a fire risk scenario. And as the political issues on flame retardants and chemicals in general, they will continue to drag on. I'm confident of this. We have millennia of human history indicating how well politics works for us. So there's a precedent for that. And I suspect also the cost of these new flame retardants, even if they're environmentally safe, will be high due to increased R&D. There is indeed a lot more that we know about environmental issues, so we have to do a lot more testing to make sure a flame retardant is safe. But predictions for the future, more good than bad. So we're likely to have better detection systems, which give us more time to escape. We'll come up with better sensors technologies that can detect even small levels of fire, giving us more time to get out. Eventually, we will have environmentally flame retardants, or maybe even inherently flame retardant, easily recyclable polymers. Why not go for the best of both worlds? But we'll have sprinklers in new construction. We may even start to see some novel extinguishing systems. DARPA has been funding some work looking at electromagnetics and sound-based extinguishing systems, where maybe rather than kind of going in with a chemical approach to put out the fire, we can effectively address the physics of the complex combustion phenomena that is fire by pulling energy out of the system or causing the gases that are flowing up to become unstable due to sound waves, and the flames just go out. But flame retardant chemists and fire safety engineers will always rise to the challenge, as they always have. I mean, flame retardant, the earliest example of flame retardant chemistry is in the Egyptian era, about 850 BC. This is an old field of study. I mean, we've been doing it for a long time. We still haven't figured it all out. Acknowledgements. So I'd like to thank the American taxpayer for funding some of my work through this particular fire grant. I want to thank my colleagues here at UDRI, especially Mary, Kathy, and John, for all their help in building apparatus for me and for doing a lot of the fire tests. I want to thank my co-principal investigator on the NIST fire grant, Vladimir Benin, for all his work in synthesis and design of the chemical flame retardants. While I'm an organic chemist by training, I haven't done the work in the lab in a long time. Vladimir is a superior synthetic chemist who's been able to look at some of the structures I've drawn out and actually make them occur, or say, hey Alex, we can get you the same chemical structure, but why don't we do this slight modification? And I obviously want to thank a variety of students that have come through my labs over the years that have helped out in a variety of projects. I mean, without their help in just every little things from grunt work and prepping samples to actually helping us burn stuff, wouldn't have been able to be successful. Flame retardant manufacturers, they've been very helpful to me over the years, giving me free samples as well as giving me technical input and advice. And U.S. government labs, Army, EPA, FAA, Navy, and NIST. And finally, anthropology. Here's an example of Homo scientificus, aka the lab monkey. It's a particularly ugly version attracted to bright lights and open flames. So thank you for your time.